Cool. So just tell me briefly, I know it was a long day yesterday and maybe you didn't have time to do it, but if you did have time to go through it in the textbook, what can you tell me about the hot oxidation? So what can you tell me about what happens when we add hot acidified manganate ions to an alkene? Just briefly, don't try to summarize the textbook, just what were the key concepts? What did you read about? Ooh, anybody? Anybody? I think we've got a bit of a delay problem. Okay. So just hands up if you can hear the question. Does anyone want to quickly explain hot concentrated solutions? Just put a thumbs up if you heard the question. Good. So you heard the question. So you heard the question, but you don't want to answer it, is what I'm assuming.
Sir, I only did physics yesterday.
Okay.
I just spent the entire day doing physics, so
okay, excellent.
I didn't get to chemistry.
So you didn't do the chemistry. Did anybody have a look at page 210 and read through the hot oxidation? Cool. So I'll take that as a no. Okay, so I'll go through it with you quickly. So what I did was I loaded it on KingDraw, and I played around with it in terms of starting materials and what can happen. So what you're going to notice is that when you have an alkene and you try to oxidize it with hot acidified manganate ions, you're not going to get predictable products. It's not just going to be an addition reaction where you just get something like the diol, for example. Cool. So here's an example where you take, oopsie, hang on, let's start with the easy example. Let's start with the first one, which is ethene. So on the left-hand side, you have ethene, and the circle in the middle here is basically just saying I'm oxidizing it. And in this case, it's hot acidified manganate ions. Ooh, and then you'll notice that the two products, they are just carbon dioxide and carbon dioxide. So what's cool about the way that I've done this is that you can actually, you can follow the arrows and you can see that this blue carbon here, so this blue carbon here ends up as that blue carbon over there. And the green carbon ends up as that green carbon, oopsie, I can bend the arrow, as that green carbon over there. Cool, so I haven't increased or decreased the number of carbons. All I've done is I've broken the double bond. And then after I broke the double bond, what did I add to each carbon?
Oxygen.
Oxygen, correct. So can you see it's still oxidation? So what I've done is I've broken that double bond, and that's what the little line down the middle means. So if you look here quickly, that line there is telling me that I'm breaking the bond. Cool. So it's a little scissor line, if you want to call it that. So I break the double bond and then I add as much oxygen as I can. Also, if you have ethene, if ethene is your starting product or starting material, and if you acidify it with hot concentrated manganate ions, you're going to end up with 2 units of carbon dioxide. Cool. And then you might ask yourself, where does the oxygen come from? The oxygen comes from the oxidizing agent, so the MnO4. It supplies the oxygen. Cool. Any questions on that so far? Just give a thumbs up if you got no questions. Yep, you good? Good. No questions there. Okay, so that's if you try to oxidize ethene. So nothing else, just ethene. There's no R groups, nothing extra, just ethene on its own. So now what you're going to do is you're going to slowly progress, and all you're going to do. Yes, Angelica, you have a question?
Yes, so the oxygens that we put in,
sure.
Sir said that we put it to the max number.
Maximum number of oxygens, correct. In other words, you fill out as many oxygens as you can possibly get in terms of the number of
So,
carbons.
for example,
Yeah,
if there was 4 carbons, just hypothetically,
yeah.
then oxygens would be 6 or 8.
You'll see more examples just now. So I'll show you more examples and then you'll
Okay.
see what's happening. But the idea is that you break the bond and you add as much oxygen as possible. Cool. So that's the key message: break the bond and add as much oxygen as possible.
Okay, thank you, sir.
So what we're going to do is we're just going to do this step by step, and all we're going to do is we're going to add an extra R group on each case. So in this case here, the only thing that I've changed, I'll highlight it for you here so that you can see it. The only thing I've done is I've added that extra CH3 group over there. Morning. Hi guys, give me a second.
Looking for Jackie's paper.
I'll find it for you. Guys, give me 2 seconds quickly. I need to find something. Okay, so again, same thing. If you look at the left and if you look at the right, I've mapped the carbons in terms of the color. So you can see here, this blue carbon is that blue carbon. And then this green carbon here is that, I can't draw a proper arrow, but that green carbon is that green carbon over there. Yeah, there we go. So I haven't added or changed the number of carbons. All I've done is I've broken them apart. And can you see with the scissor, I've just taken that carbon, I've broken the double bond. Cool, and then what did I do to the double bond afterwards?
Only one double bond was broken.
One double bond was broken, correct. And then after I broke the double bond, what did I add to the carbon that the double bond was broken at? So what's the rule with this process? Break the double bond and then
Add the oxygen.
add as
the
much
OH.
oxygen as possible, correct. So it's quite it's an analysis project that you need to, these are all in the notes. I've summarized this in the notes. It's an analysis project where you have to say to yourself, once I've broken the double bond, in what positions can I add oxygen? And in the case with the CH2, if you look over here where there's a CH2, I can always add 2 double bond oxygens because there's nothing else bonded to that carbon. Ooh, and then what you'll notice with the other one. Yeah, talk to me. What you'll notice with this one over here is that that CH group stays. So I don't change that. And what you'll notice here is that the only thing that got changed was, oopsie, in that arrow. There we go. That H over there became an OH. But would you agree with me that in the position of the double bond, I just added an extra double bond O. So I replaced the double bond carbon with a double bond O. And then I replaced the hydrogens with an OH.
Yeah.
So you need to go home and you need to analyze these things. It's not as straightforward as you can look at the reactants and you can look at the products. You've actually got to sit down and slowly go through it page by page, even if it takes you 5 to 10 minutes to go through each page. You've literally got to color them in and convince yourself that there has been a change and what is that change that happened. So if you look at it this way, I can show you another way to look at it. I can do this. And I can superimpose them. Oopsie, no, don't do that. I can superimpose them. I can move this one over. And can you kind of see there that in this
So I have a
case,
question, Chris.
yes?
So where did the C go? The H2C, that C.
That became
the
correct.
blue C.
That became the second. That became the double bond O on the left-hand side. So
so these are 2 different, those are the products. Okay.
those are the products, correct. Left-hand side is reactants, right-hand side is products. So if you look at that, these hydrogens here became that oxygen there. Cool. And then the double bond is where you broke it and you added oxygen to the double bond. So where there's hydrogens, you add oxygen. Where there's a double bond, you just add a double bond O. And if you superimpose them, if you put them one on top of the other, you'll see that that kind of looks like the starting material, except that the two H's that you mentioned, the blue ones, became, let's do it like this. Those ones became these ones, and that hydrogen there became that OH over there.
I understand that one hydrogen went to the OH. Where did the other hydrogen go again?
It became the OH, and then the CH2 became the double bond on the left. So let's see. Okay, so I'll draw an arrow. This CH2 became that oxygen there. This H over here became that OH over there.
Okay.
Sir, isn't water formed as well?
No, yes, water, but not as a byproduct of the oxidation. It's formed as a byproduct of the manganate ions reacting with the acidified solution. So water is an irrelevant product because it's kind of like a waste or it's kind of a byproduct of the reaction, but we're not interested in it. There are other byproducts here because the manganate ions would form a different form of manganate ions. So the Mn2 plus and stuff would all be left in solution. But would you agree with me that the important part are the functional group conversions that we're interested in?
Yeah, but you can form other functional groups. You can maybe not just have carbon dioxide and a carboxylic acid.
Exactly,
but also like other-
exactly. So if you read page 210 and 211 yesterday, you would have seen that we can form ketones as well. So that's the next example. So the next example here is if I take this molecule here, it has the CH2 on the left-hand side, and it has two methyl groups or two CH groups on the right-hand side. So I'll switch it to this view over here, then I can edit a bit better. This one over here, and we can edit that. Cool. So let's map this and see what goes where. Cool. So the blue carbon stays the blue carbon. Cool. And these H2s over here became that O over there. Cool. The double bond stayed the double bond, so the double bond didn't change. So this double bond here in the middle is still that double bond there and that double bond there. And then you'll see that this carbon over here becomes that carbon over there. Cool. And then what functional group do I have on the right-hand side? What's the name of the functional group? Don't worry about naming the molecule, just identify the functional group. Ooh, anybody? What's the functional group?
This one, so which one?
On the right-hand side, so this one over here. What's that functional group?
Ketone.
It's a ketone, correct. So guys, by now it's been 2 weeks. You should be able to spot a ketone almost instantaneously. So by now, this already should look like a ketone. Cool. So you need to revise your functional groups and make sure that you can identify a ketone. Cool. And then this molecule on the left is obviously just carbon dioxide.
So are the two blue hydrogens just lost, or?
They're not lost, they get converted to oxygen. So it's a very good question. And the answer is wherever you have additional hydrogens, you convert it to oxygen. Cool. So whatever hydrogens are bonded to the carbon, you turn them into oxygens. So in other words, these two hydrogens here become that oxygen over there. Let's not call it change, let's call it replace. Cool.
Yes, so if when it replaced it, where is it now? Is it in the air
Yeah.
like is
It's part
hydrogen or-
of, correct. So what Stefan said earlier is absolutely correct. It probably becomes water. So it gets removed off the carbon and it probably bonds with oxygen to form water. But we're not interested in those byproducts because water could be a byproduct of all the reactions. So the important thing here is the product that we can form, or the carbon containing products. And then this carbon here becomes that carbon there. Cool. And would you agree with me that where the double bond, carbon-carbon double bond was, we just replaced it with a double bond oxygen. So do you notice that there's always a double bond oxygen? Like we can't get away from adding a double bond oxygen. Yeah, everyone happy with that? Can you see that we can't get away with adding a double bond oxygen? Yep. So we always add a double bond oxygen. So let's have another example. Let's have a look at this example over here. Cool. So forget about the left-hand side. Just look at the right-hand side. Would you agree with me that that's the same molecule just rotated? So everyone agrees.
Yes, sir.
And then what functional group do you see?
Is it carboxylic?
Correct. So it's carboxylic acid. So you notice it instantaneously by the C double bond O and the OH. That's the carboxylic acid. Cool. So by now you should have well, it's been 2 weeks, so it should be almost instantaneous to recognize something like that. Cool. And then let's map it and see what's going on. Let's look at the blue one. This blue carbon became that blue carbon, and the hydrogens that were on that blue carbon, these ones over here. Oopsie, I looked at that one. These blue hydrogens over here still stayed those blue hydrogens over there, and this blue hydrogen over here became the OH.
So how do we know that it's going to move as OH, but it's or that it's going to be lost as water? Like, how do you know if it's going to?
So it's okay. So the rule is quite straightforward. Wherever you see an H, replace it with oxygen. If you have 2 H's, for example, you can replace it with a double bond. If you have only 1 H, you have to replace it with OH. But would you agree with me that there's always a double bond formed? If you look at that double bond in the middle is the same as that double bond, is the same as that double bond. If you literally just separate the molecules, and then you can map it and you can say this hydrogen became that OH, and that hydrogen became that OH. Cool. Would it be possible to add another double bond O to that carbon? Would it be possible to add, I'm going to show you here, would it be possible to add over here a double bond oxygen and get rid of this hydrogen? Would that be possible? So would that be possible like that?
No, sir.
No, not possible. Why? Because it has 5 bonds. So that has 5 bonds. So can you see that in order to keep 4 bonds, I can't add another double bond O. I can only add an OH. It's my only option. So the only option is to replace the hydrogen, this one over here, with an O. And don't worry about the byproducts. The byproducts are irrelevant. All we're saying is that whatever additional hydrogens you have on the carbon, take them away and replace them with as much oxygen as possible. So take away the hydrogen and replace it with as much oxygen as possible. Cool. And then would you agree with me the rest of the molecule stays the same?
Mm-hmm.
Yeah, so I haven't changed anything else. All I've done is I've shifted it. And if you really want to, you could draw a line and say, if my starting double bond was that, you could actually go back and reform that molecule and say, there's my double bond. Can you see I've just stretched them apart. I've just pulled them apart. So I pulled them apart and I replaced the H's with OH's, and I replaced the double bond C with the double bond O. So that's basically all we're doing. We're stretching the molecule apart. We're replacing the double bond C with the double bond O, and then we're replacing hydrogens with OHs. Let's have a look at another example. Where's a different one? There's a different one. Oh no, hang on, we did this one. Let's go back. Where's the one that we haven't done? Let's look at this one. Here we go. Cool. So let's do that. What we said last time. Let's do it exactly how we said last time. So here's the double bond here, which means that's the double bond there. So that's all we did is we took that double bond apart. We literally just stretched the molecule. Cool. So we broke that apart. And then what we did is we replaced the double bond with O's on each side. So I've added those two O's over there. So I've got that oxygen and I've got that oxygen. And then whatever hydrogens are left over on the carbon, we replace with OHs. So if you look at this one, that there becomes that there. And I have no hydrogens on the blue carbon, so I can't replace anything on that side. And then you've got to name the functional groups. Don't worry too much about naming the molecule, but what do we have on the left? And sorry, not the left. Let's call it product 1 and product 2. Let's call you 1 and let's call you 2. What functional group you have in product 1?
Aldehyde.
Almost. Cousin of the aldehyde.
Isn't it ketone?
Ketone, correct.
Oh,
so that's
well, sorry, I thought it was hydrogen.
It would have been a hydrogen if we didn't fully oxidize it. Sorry, that's a lie. The right-hand side could have been an aldehyde if we didn't add the OH. Cool. And then the right-hand side is what?
Carboxylic.
Correct. So that's a
Carboxylic
carb acid. Yeah. So we have a ketone and a carboxylic acid. So we have two asymmetrical, sorry. We have two different products. We have a ketone on the left and we have a carboxylic acid on the right.
So
Hello.
the only difference between an aldehyde and a ketone is it like on which carbon the oxygen is?
Correct. So if you've been going over this daily, you would have realized that your aldehyde always has the OH double bond O on the last carbon. So your aldehyde would be this one over here. So the aldehyde has the OH, not the OH, the double bond O on the final carbon. So in actual fact, they're related to each other. They're members of the same family, if you want to call it that. They're called carbonyls. Together, they're called carbonyls. And then you'll see later, we separate carbonyls into ketones and aldehydes. So we can go back and then we can go look at the final one. And the final one is where you have everything fully substituted like this. Fully substituted meaning there's no extra hydrogens. So let's highlight the double bond. There's the double bond there. And we basically stretched the molecule apart. So we just pulled it apart by the double bond. So we pull that apart. And then we try to look for any hydrogens that were floating around. So let's look for hydrogens. There, no hydrogens. Look at the other one. There, no hydrogens. So in other words, I can't add another OH here. So I can't add additional OHs there. Good. And then what type of products do I form in terms of functional group?
Two ketones.
Correct. So we have two ketones and they're identical. So 2 times ketones that are identical. In other words, we have 2 of exactly the same product. You can take the other one and you can rotate it. So if you go to your drawing program, you can take the molecule, let's see where it is. This one over here. You can take the one on the right-hand side and you can literally just flip it over. So you can flip it, 180 degrees. And you end up with exactly the same molecule. Cool. So just for a summary, just in terms of what's possible, if you get given a double bond, and we're going to call these R groups where R can be either carbon or hydrogen. So R is either carbon or hydrogen. What are the only three possible outcomes if you oxidize the bond? So if we oxidize it, what three products are possible? Not the names of the actual specific products, but the types of functional groups that we can get. And one is not strictly speaking a functional group, it's just a molecule.
So, an aldehyde.
No aldehydes, because we always fully oxidize aldehydes to form the next level. So what's
Is
there?
it two ketones?
Possibly two ketones, but you can get ketones correct. Ooh, so you can get
Carboxylic
ketones.
acids.
You can get carb acids, correct. And then the one that's not really a functional group, but it's just a molecule. What molecule can you
Carbon
also form?
dioxide.
Correct, carbon dioxide. Oh, it's glitching now, so I'll stop the meeting and then we can go
Ethanoic
again.
acid.
Ethanoic acid is a carboxylic acid, correct. So we're saying that we can form ketones, we can form carboxylic acids, and we can form carbon dioxide. Cool. So when we break the double bond and we oxidize it, we can form a ketone, we can form a carboxylic acid, or we can form carbon dioxide. Cool. So that's basically what was in the textbook 210, 211. And what I told you to do yesterday is make sure that when you read page 210, you've got to link it to what's on page 211. You've got to sort of put them side by side. Well, they are side by side in the textbook, luckily. And you've got to basically, in your own notes, make sure that you understand that there's a link between page 210 and page 211. Cool. So just before we end the lesson, let's do a quick example. And when I say quick example, I just mean we're not going to try and fully understand the problem. All we're going to do is say, based on the structure, are we going to get a ketone, a carboxylic acid, or a carbon dioxide? So you're going to have a double bond here. And then I'm going to draw something odd, just randomly on that side. And then just for interest's sake, I'm going to put a chlorine. Do we have to focus on the chlorine? Is it relevant to our problem?
No.
No, we don't have to
Unless we
focus on the
form a
chlorine.
halogen.
Correct, unless we're doing some sort of functional conversion that involves halogen. So in other words, we're only really interested in that carbon and that carbon. And then the question is, if I break them apart, that carbon will become something and that carbon will become something. So I can break them apart. And then just remember in the back of your mind that there's a hydrogen here. I don't have to draw it, but I can put it there just to show you that it is there. Cool. So if you have two hydrogens present, what's the only molecule you can form?
Carbon dioxide.
Correct. So that side's going to give you carbon dioxide. And when you have one hydrogen present, can you form the ketone or do you form the carboxylic acid?
The carboxylic acid.
Correct. So this side will become a carb acid. Cool. And I'm not going to say it's as simple as that, but it really is as straightforward as just saying, if there's two hydrogens, it becomes carbon dioxide. If there's one hydrogen, it becomes a carboxylic acid. Cool. So if we look at another example, draw that like that. Just make that an R group, make that a tricky one with a bromine over there. And then put two groups over there. So CH3, CH3. And then look at the two carbons on this side and on this side. And I'll just remind you, there's one hydrogen over here. Cool. So what would this carbon become? Left-hand side.
Carboxylic acid.
Correct. So that becomes carb acid because there's one hydrogen. And on the right-hand side, there's no hydrogen. So I can't form carbon dioxide, obviously. Can I form the carboxylic acid?
No.
No, sir.
So it has to be the ketone.
Yeah.
Cool. And when I say ketone, I don't mean, well, in this case, it is going to be just a ketone, but on the left-hand side, it's going to be a carboxylic acid with the bromine attached somewhere in the molecule. But it's not the molecule's name. That's a carboxylic acid. It's a functional group that's present in the molecule. Cool. So these are functional groups, not molecules. Cool. So carboxylic acid is just a functional group inside a molecule. Cool. So guys, we'll end the meeting there. And then in the next lesson, we'll do polymerization. But all these notes are in Google Classroom. You can go and have a look at them.
Thank you, sir.
Good. See you guys
Yes,
just
sir.
now.
Thank you.
Be back in 10 minutes. Go take a 10-minute break.
Okay, sir.
Cool. 10-minute break, and I'll see you in 10 minutes.